Hey class, it's pretty late at night, still not feeling 100%, but let's do this anyway. So continuing on last lesson about enzymes, so we found out that enzymes, they're affected by temperature. The higher the temperature, the faster the enzymes move, and the more collisions per unit time, so then we get a higher reaction rate. There is an optimal temperature, so when the temperature is, say, around body temperature, if we're talking about enzymes within a human body, the optimum temperature is about 37 degrees. That is when the enzymes move around the fastest, and we have the fastest reaction rate. However, if the temperature goes over say 45 degrees, the proteins, the enzyme will denature, it will lose its shape like so, and will no longer be able to bind to the substrate, so there will be no reaction at all. Reaction rate will be absolutely zero when it goes past say 45 degrees or past the point of denaturation. Sorry, I'm just going to cough. Okay, so today we're going to be looking at how pH affects enzyme activity. Most enzymes work around a pH of 7. There we go, nice purple color. 7 is neutral. Actually, I do not want to use purple for this. I want to use green because 7 is neutral, and we often see this as green. Okay, my pen isn't working today, but anyway, 7 green. Okay, that looks like a 1. Okay, pH is 7. 7. There we go. pH of 7. This is because the pH inside the cell is usually between 7.2 and 7.4 pH. You do not need to remember that. You just need to remember that most enzymes work best around the pH of 7. Under highly acidic, so let's use a red. Okay, so high acid or high alkaline conditions. Remember, this is pHs, which are, or alkaline is, high alkaline will be somewhere between 12 to 14. My computer's lagging on me, but it's okay. Or high acidic, or high acid conditions, they'll be between 1 and 2. Between 1 and 2. High alkaline conditions between 2 and 14. The shape of the enzyme will be altered and be less productive. So at these high acid and high alkaline, the shape of the enzyme will also be altered. Another word for that is denatured. Okay? Yeah, my pen's not working. Denatured. Let's try not lift it off. There we go. Okay, so the enzyme will be denatured. Again, that is a loss of shape, especially in the active site. If the active site no longer has a shape, it can no longer function. So get these notes down. Cool. Moving on. Here we go. Nice, easy graph. So over here we have denaturation again, or denature of enzyme. Okay, and on this point over here we have the denature of the enzyme as well. Here we go. Okay, so there's denaturation of the enzyme on both sides of the bell curve. Okay, so at both extremes. According to this graph over here, if the pH is below 5, okay, so this is highly acidic. Okay. Okay, don't worry, I'll make sure I change my pen for the next I'll make sure I'll change my pen for the next video. Acid over here, if the pH is very acidic, okay, so under 5, it's going to denature. If the pH is over 10, so this is alkaline. Well, no, this is not working. So this is alkaline, okay. It's going to denature as well. I might actually try to use the mouse for this later on. It's going to denature as well. So here we go, and this is the enzyme activity. At the top, at a pH of 8, okay. Remember, the pH is so for this particular enzyme, it works best at a pH of 8. I just stated before in my last slide that most enzymes work best at a pH of 7, but there are different enzymes, and different enzymes work at different pHs. One moment. Okay, so remember, there's a whole heap of different enzymes. Enzymes are used to do a lot of different things. So, although so here are 3 enzymes. What I've got is pepsin. So pepsin over here. I have salivary amylase over here, and arginase. So there are 3 different proteins. 3 different enzymes, which are proteins as well. So, but there are 3 different enzymes. Salivary amylase is an enzyme within your saliva. Because the enzyme is within your saliva is quite neutral, so it works best in a neutral situation. It works best when the pH is 7. Pepsin, on the other hand, okay, pepsin is an intestinal enzyme. In your intestines, you've got a high concentration, a high pH, so acidic conditions within your intestines. So pepsin works best in acidic conditions. So it has an optimal pH. So here's its optimal. Its optimal pH will be at 2, at a pH of 2, whereas pepsin has an optimal pH of around 7. Arginase, this is another enzyme which you will not be tested on. You won't be tested on these enzymes either, but arginase is another enzyme, and it works best in basic conditions. Okay, so other enzymes like pepsin have different optimum pHs and ranges. However, the shape and function will change if the pH goes outside of its range. So it will still denature. It will still denature if it goes outside of the range that the enzyme can work in. Okay, moving on. So we've already covered 2 conditions that will affect the rate of reaction of enzymes. Here's another one: substrate concentration. The more substrate, the more collisions, the greater chance that the substrate will bind to the enzyme. So this is all about collision theory. I have a whole heap of enzymes. Let's see if I can draw some enzymes. Cool, there we go. I have a whole heap of enzymes. I think 3 enzymes, that'll be good enough. Okay. And we'll make this a catabolic enzyme. Oh, we'll make this catabolic anabolic. It doesn't really matter. We'll make it. We'll just have a whole heap of substrates. Let's see if I can draw a ball. There we go. Okay. Let's erase one of these. let's just have one. Okay, so here we go. So the more substrates, the more collisions. So if I only have one substrate and 3 enzymes, what's going to happen is that this substrate will keep on bouncing around. Okay, so it'll be moving around, it'll be bouncing around, and these enzymes, they will be moving around as well. Okay, by random chance, these enzymes and this one substrate will end up colliding with one another. Once they collide, they will react, and the reaction will happen. So we've got a rate of reaction once they collide. If I increase the substrate concentration, so if I increase the particles, increase the number of substrates per volume, so let's just add another little ball, and this ball, it's also going to be moving as well. Okay, so now I've got 2 substrates. So say this one bounces, falls into this enzyme here, this one, it flies and falls into this enzyme over here. If I can draw an arrow, there we go. So they both fall into the enzyme, they bind to the active site of the enzyme, and a reaction occurs. Since there is 2 substrates instead of 1, it's going to happen twice as fast. Okay? If I add a 3rd substrate, same thing's going to happen. Okay? The more substrates I add, the more collisions, the higher the reaction rate. Okay? So this is number 3. This is going to fly, and it's going to go into this enzyme here. Now the problem is, if I keep on increasing the number of substrates, so if I increase it to number 4, if I add another substrate within this concentration, it's got nowhere to go. So this is represented by this X here. This is the point of saturation. 3 is the point of saturation. This means that all of the enzymes are working as fast as they can with the substrates which are present. If I have a 4th substrate, the rate of reaction is not going to increase. It's only going to go at, say, 3. It's going to only go at 3 reactions every second if these reactions take 1 second. Okay. However, so if I keep on adding more substrates, it's still going to be 3 reactions per second. It's not going to increase past this point of saturation unless I increase the number of enzymes as well. So moving on, don't cough again. Yay, cofactors. Interesting. Okay, I'm sure I got another slide about cofactors over here. Here we go. Okay, cofactors. Cofactors are something that needs to be bound to enzymes to make them work. So here's a picture. So cofactor, it's a non-protein portion. A good example for cofactor is magnesium. Okay, a magnesium ion. Often, for some proteins to work, okay, they need a cofactor. The cofactor is normally non-protein. So example, a magnesium ion, and that will fit within the enzyme and change the structure so it will work. Without this cofactor, the enzyme won't be able to work, the substrate will not be able to bind, and there will be no reaction. So if it's an enzyme that requires a cofactor, the cofactors must be present within the cell, within the organism, for it to work. Okay, and lastly, inhibitors. These are really cool things. So inhibitors, they're chemicals that prevent enzymes from working. So what they do is they bind. They bind to the active site and they don't let go. They pretty much just completely block the active site. Okay, so here is the normal reaction. With this, I've got one substrate and it's breaking into two substrates. It's breaking into two products. Remember, this is a catabolic reaction. So one substrate binds into the active site, breaks off into two substances, two products. This is a normal reaction. However, inhibition, okay, is when an inhibitor, it comes in, binds to the active site, okay, and just completely blocks the entering of the substrate. So it can't bind. So this is a very common mechanism. And yeah, so if I've got a high concentration of inhibitors, my rate of reaction is going to be very, very low. Cool. So that is all of enzymes. Yeah, that's all of enzymes. That's pretty cool, eh?